from this slide is that fresh water that we are drinking, this fresh water we are drinking, it is a scarce resource. It's a very, very scarce. Okay? Says, if you look at that, I don't know why this, but in any case, about 2%, 1.78 or 2% of the total water on the planet is fresh water. So what does that mean? Let's say in this bottle, all of that water is the total water on our planet. Let's assume that. This is the total amount of water on our planet. Fresh water is one drop of this. That's it. Everything else is what? Salt water. Okay? It's only 1.78%. And that number has not increased in the last 2 million years. So we're not going to get more fresh water from anywhere. So it's very less, about 2%. And out of the 2%, a lot of that, 50 to 60% is on glaciers. It's locked in glaciers. And the remaining is what we use in agriculture, industry, and urbanization. We go to the bathroom, we turn the water on, it runs. Every time that water is running, you have to remember it is a scarce resource. Okay? Some regions have plenty of water, some regions don't have. See here, this is how it is distributed. Australia has got only 4% of the total fresh water. It's a very dry continent. Entire central Australia is big desert. Okay? Asia has got 36% simply because it's the largest continent. 8% in Europe, 11% of the fresh water is in Africa. US, North America, sorry, has 15%, and South America has got 26% of the total water. This is how it is distributed. But it's a very tiny, tiny fraction, scarce resource, and we should all be responsible when we use water, fresh water. We are already polluting it with all kinds of things. And one day we'll run out of that fresh water. There is no agriculture, there is no industry. You may not take shower every day. That's the situation you'll end up with. Okay? Yeah? You have something to say? Go ahead, tell me. You agree to that? Yeah. What is he saying? He said something in Hindi, I can't understand. So. What was he saying?
We have to save water.
Yes, of course we have to save water. He saves it by not taking shower. Good. Just kidding. All right. No, do take showers. Okay, but just be responsible. Right? There is a limit, right? Something like that. But I'll say this: most of the wastage happens in developed countries. Okay. In developed countries, people are lavishly using water. Right. So I think it should start there. But also keep in mind, countries like India are more prone to water-related issues than other countries. So you got to be very careful. Okay. Any case, this is the distribution of water, and we're going to talk about water. And in this chapter, I'm going to do. I think this chapter is divided into two sections. One is more about water itself, the properties of water, why that is important, what is it that in that water that makes it important for plants and everything. And then we talk about irrigation. How do you apply irrigation? We talk about timing irrigation, frequency of irrigations, measuring water that you're applying, sensors that you use to apply or measure water, things like that in the second chapter. The first chapter, like always, is about basics.
There is no difference between the normal water and fresh water. The water comes to the sink and all. That it's the fresh water, drinkable water.
No, it's separate.
Because I saw some videos in California and other places there.
Oh, you mean? Okay, so I'll explain. So you get the water. So there are a lot of sources of water. Like here we have city water, we have well water. They are also in the US. But where I live, I get city water. And the city water is only one source. Okay. But then it gets into two purifiers. Those purifiers are something that we purchase and build in our homes. One purifier is just for urban use, like in bathrooms, for in kitchens if you want to wash. The other one is for drinking purposes, where you got 3 or 4 separate filters, bacterial filters, and you have filters for different things. So that is connected to a separate tap, and so you'll have a tap for drinking water, and the rest of the stuff is different. Yeah, yeah. It does come through one pipe into the house. Yeah. And some people don't care, they just drink it. It's not good. There's a lot of iron because some of the pipes are very old, and you will see yellow, brownish color water sometimes. That's because the pipes are, there's a lot of iron that is rusting inside and that's coming through water. So you got to be very careful. We also have the problem of nitrates in the water, even in the United States. Yeah. Well, in case, let's move on. The first thing is a little bit of physics here, not too much. So don't get too worried about it. This is the water. So what is the formula for water? Everybody knows it, right? H2O. You see that? H2H. This is O here. H2O. But what I wanted to really focus is that angle. That's important. See, it's not like HOH, not straight line. It's at an angle. That is the secret of life, by the way. This is the secret of life. I'm telling you the truth. Let me explain. If water is like HOH, straight line, it is neutral. There is no charge on it. But because water is like this, 2 H's on one side and O on the other side, it's got a negative and a positive, slight polarity is there. This small charges, negative on the oxygen side, positive charges on the hydrogen side, that makes water polar molecule. That is the reason everything is soluble in water. If nothing is soluble in water, we don't exist. Plants don't exist. This angle of 105 degrees between hydrogen and oxygen is a secret of existence of life on this planet, to be honest. Okay, so important. Remember that. That is what makes the water a polar molecule, is slightly negative and slightly positive, so it attracts. All molecules get attached to it, become soluble. All of that happens because of this. That's what I want to get out of this particular slide. You see, right there I mentioned, instead of 180 degrees, it is 105 degrees. Okay? This creates an electric field, right? You have a negative and a positive, and within that electric field, everything happens. Attraction, repulsion, other ions get attached to water, they become soluble. All reactions are happening. That's the secret. Okay? So here is again that this one water molecule, this is another water molecule, 2 molecules. Again, you see the 105 degree angle here. There is also another 105 degree angle here, right? So I'm just explaining. Hydrogen and oxygen are attached through covalent bonds, ionic bonds, and then hydrogen and oxygen of another water molecule, they're attached by a hydrogen bond. It's a weak bond. Okay, that's how water molecules attach with each other, weak hydrogen bonds. Just remember that hydrogen bonds. Okay, but that's nothing, simple. This is the concept of pH, and I want to spend some time on this slide. Okay, so what is pH? pH tells you whether the water is acidic or basic. As simple as that. There is a formula for that. It is measured as a negative logarithm of hydrogen or hydronium ion concentration, right? But what is the origin of this pH? Where is that acidity or basicity coming from? That is explained here in this particular cartoon right here. You see this one? So what's happening here is, so this is one water molecule and this is another water molecule. Normally speaking, there are 2 water molecules here. But what has happened here? A cleavage has happened, a break has happened where this hydrogen, which is supposed to be belonging to this water molecule, is pulled away from it and is now attached to the second water molecule. Can you see that in this picture? Right? This hydrogen, this oxygen, and this hydrogen should belong to one molecule. Here is another water molecule, but instead this particular one was pulled away from this. Now what have we created? We have created a OH minus, and here we have created a H3O plus to separate ions now. Before they were H2O and H2O, but now this thing got separated and got attached to this molecule and it made H3O plus. H3O plus is nothing but H plus or your pH. This is where you are getting the pH of water. If there is more of this, it is basic in nature. If you got more of this H3O plus, you have acidic nature. That's how the pH originates. It's because of that breakage of some of the H plus atoms from one of the water molecules and attaching to another water molecule. And this happens in millions and millions of molecules inside a bottle of water. And that's why you get either a basic or a pH nature, or acidic nature. This is the origin, this is the theory of pH basically. We say it is a negative logarithm of hydrogen ion concentration. No, it is in reality is a negative logarithm of hydronium ion concentration. H3O plus, hydronium. But for simplicity, we'll simply say it's negative logarithm of H plus concentration. But it's hydronium, not H plus. Okay? Either way, it's okay, but that's what it is, hydronium. Here is your hydronium, and that is causing the pH of water. And how is this hydronium formed? When one of these molecules from another water cleaves and splits and gets attached to another water molecule, it forms H3O plus. Okay, some simple concepts. Okay, but again, pH is negative log H plus concentration. We abbreviate H3O plus as H plus. That's why it's H plus. But in reality, it's that hydronium. That's what causes pH. Okay, just remember that pH. Now here is the three states of water. Water exists as liquid, right, ice and vapor. But I want to show you how the molecular structure is. Again, look at it. This red one is oxygen and two hydrogen ions, right? Like a tiny mouse ears, right? Again, these are all water molecules. Each one of them is a water molecule. But in the vapor state, the water molecules are all flying everywhere. When you get to the ice, you see a structure there, a disciplined structure there, a crystal-like structure. And then when you get to the liquid water, it's all everywhere. There is no structure or nothing. Ice floats on water, right? Ice floats on water. When you add ice on water, it floats. Why is it floating? Because of that structure. You see open gaps in that structure? There's a gap here, there's a gap here. Nothing like this. This open gaps makes ice lighter than water, liquid water. That's this molecular structure that makes it float, makes ice float on water. Okay. Otherwise, we don't have any Arctic ice, right? If you go to Arctic, there's all ice over the ocean. Heavy, heavy, big mountains of ice, they're still floating. Why? Because of that open molecular structure. Okay. Here is, I think I kind of talked about this, but let me re-emphasize. For water to move from one place to another place, it requires a pressure gradient. Water moves from a high pressure area to a low pressure area. Okay, it is happening simply because there is more pressure of water in one region versus another region. Take soil. The entire soil is dry. You pour a lot of water on one side. Eventually what happens? The water slowly moves everywhere and stabilizes. How is water moving? What is causing that movement? It is that pressure gradient. There is no water here, less pressure. There is a lot of water on this side, more pressure. So water moves from more pressure to less pressure. That pressure gradient is what causes water movement in the soil. Okay. Remember pressure. Pressure is the important word. Okay, water pressure. See, water flow is water pressure gradient divided by resistance to flow. But this is important. Pressure gradient is what makes water to move from one place to another place. These are all some simple concepts. Eventually, I'm going to use these concepts in explaining you some concepts related to how water moves from soil into the plant and outside. Okay? But remember pressure. Pressure is the secret. All right. Why? Okay. So now we come to an applied term, volumetric water content. Okay. we measure the amount of water in a pot or in a substrate or even in a soil using a measurement called volumetric water content. Okay, it's very easy. Uh, Again, let's go back to our 1 liter example. Okay, container with 1 liter, we got cocoa peat, coir in that, right? So the volume of the medium is what? 1 liter. I'm going to take now a beaker. Beaker has half liter water, 500 milliliters, and I pour that water into that 1 liter medium uniformly. I'm assuming that none of the water is leaking out, but so how much water is there in that pot now? Well, water, how much water is there? See, it's to begin with, we had 1 liter of the substrate, and then we added half a liter water on top of that. So how much water is there in the substrate now? Half liter, 500 ml. What is the volume of the substrate? 1 liter. No, 1 liter. Substrate is 1 liter, right, to begin with. Substrate is 1 liter, water is 500 milliliters. So volumetric water content is 500 divided by 1000, 50%. Simple. So the reason why this measurement is useful is we have some sensors that tell us volumetric water content in a pot. You put the sensor inside and you can measure it. With that measurement, now you can tell approximately how many milliliters of water is there in that pot when you know the volume of the pot. Let's say the volumetric water content comes out like 35%. The sensor tells you 35%, and you have a 1 liter pot, immediately you can say, oh, it looks like in this pot there is 350 milliliters of water. That is the nice thing about this measurement, volumetric water content. So what is the definition of volumetric water content? It is a ratio of volume of water in the substrate to the volume of the container or volume of the substrate. The volume of the container was 1 liter, the volume of the substrate was 1 liter. We added 500 mils of water, so it's 50 by 1000, 50%. Or it can also be written as 0.5 meter cube per meter cube. Do you know the units for volume? Volume is measured in meter cube or centimeter cube. So the numerator is volume of water, that is meter cube. The denominator is volume of substrate, that's also meter cube. So in this particular case, it's 0.5 meter cube of water per meter cube of substrate. Do you want me to repeat that one more time? How I got it? Yeah, because top one is water, the bottom one is substrate. They are not this. I know this meter cube, and you want to cancel them out, but that meter cube is coming from water, the bottom denominator is coming from substrate, so we want to keep it aside. Yeah, if you want to take the meter cube per meter cube out of this, you have to express this percentage. The percentage is, what is that? 0.5 is equal to 50%. Okay. So volumetric water content, again the definition is volume of water to the volume of substrate or volume of container. The units are either percentage or in meter cube per meter cube, or you can also say centimeter cube per centimeter cube. They are all same. Okay? Because the volume is measured in meter cube or centimeter cube. All right. So look at this. This is a container, right? It's a pot. All right. So how do you measure? In this case, look at this. This is the height of the substrate in the pot. Brown color is your substrate. The height is h. Okay. The radius of the pot at the bottom is r1, at the top is r2. So how do you determine the volume of substrate in this case? Right? So the way we do that is, we first determine the average radius. Average radius is r1 plus r2 divided by 2. You get an average radius. You take that number and then calculate substrate volume as pi r square h, like a cylinder volume, where r is that average radius. Does it make sense? Let's say if this is 4 and this is 6. What is the average radius? 5. You take that 5 and let's say this height is let's say 10. Okay. So average radius is 5, height is 10. You come back, you do pi r square h, 3.14 times 5 times 5 r square times 10, which is the height. That is the volume of the substrate. That's the denominator. Okay. And then how do you determine the volume of water you are adding? What you normally do is, you take pot, substrate in it, you weigh it. You get, let's say, W grams, W1 grams, let's say that's W1 grams. And then you add water, and then you weigh it again. It's W2 grams now. What is the difference between W2 and W1? And when you subtract wet weight from dry weight, you get what? Weight of water. So you get weight of water in grams, but you have to assume that 1 gram is equals to 1 milliliter, right? Because 1 liter of water, which has got 1000 milliliters in it, it weighs 1 kilogram at room temperature. So approximately 1 gram is equals to 1 ml, 1 milliliter. So here it is. So once you get, fresh weight and dry weight, and you get milliliters of water, 1 milliliter is equal to 1 centimeter cube, by the way. Very simple. 1 milliliter is 1 gram is equals to 1 ml, which is also equals to 1 centimeter cube. Okay. You want to check that on Google? Yeah, it looks like you have a doubt, but you can check it on Google. In 1 liter you have 1000 centimeter cube, right? So 1 ml is 1 centimeter cube, right? So that's how it is. So 1 gram is equals to 1 ml is equals to 1 centimeter cube. You got pi r square h, the volume of substrate, in centimeter cube. When you multiply them all three, see, r square is a centimeter square, h is in centimeters, so multiply, you get centimeter cube. And you get here the water also in centimeter cube. Divide the centimeter cube of water divided by centimeter cube of substrate, you get volumetric water content. This afternoon you will do an example mathematically, so you will know exactly. But that is volumetric water content. This is a measure of amount of water in a pot. Simple. How much percentage of the pot volume is water? That's it. Okay. Simple concepts, but later on we'll use all of this when we get to that. And here is where everything gets really, really difficult. So I want all of you to take a little bit deep breath for 1 minute, because we're going to dive into a really complicated concept. But I cannot, avoid it. We have to go over this. This is like the difficult part of this chapter. We're going to jump over that. But I'm going to talk slowly. I'm going to explain everything. Okay. Remember, I said water moves from one place to another place because of what? Pressure gradient, right? High pressure to low pressure, right? That volumetric water content I just described to you, of course, it's a measure of how much water is there in the pot, but that's for our convenience. Okay. So for example, let's say here is you take volumetric water content measurement in this region and in this region. Let's say you have more volumetric water content here and less here. It still doesn't mean that water is going to move in this direction. Okay, it still doesn't mean that. There could be other things. But if I'm talking about pressure, more pressure and less pressure, definitely water moves in this direction. We developed volumetric water content for our convenience, just to know how much water is there in a pot or in the soil or in the substrate in milliliters, because we understand milliliters very easily. 500 milliliters with 300 milliliters, we can even imagine it, right? But if I talk about, the water here is minus 4 megapascals and the water here is minus 2 megapascals, you are going to look at me, what do you mean minus 2 megapascals, or what do you mean by minus 5 megapascals? We get confused. The term is confusing. So for our convenience, we created volumetric water content, and it is all in milliliters and easy to interpret. If I say that this pot has got 500 ml of water, and you look at, there's plenty of water, 500 milliliters is a lot. So it's for our convenience we created that. But when it gets to plants, when it gets to a real deal, water moves from one place to other place, and water has to be measured in water potential units, the pressure units. So water potential is nothing but pressure. Okay. Now, as I'm explaining this, some of you may follow everything, some of you may not follow everything. It's still okay if you don't follow everything. If you get little bit bits and pieces, little bit understanding of what this water potential is more than enough. Understand? Okay. There is something later on I will talk towards the end of this slide, or maybe on the next slide, what I call soil plant atmosphere continuum, and that is something I wanted to really understand. Okay. But in any case, so what is water potential? Water potential is nothing but pressure of water in any location. It is measured, the problem is that it is measured in negative values. I've shown you the graph, right, with a negative number, minus megapascals. It's measured in negative. That's what confuses everybody. That's what really confuses everybody. So what it means is, let's say the water potential in this point is minus 2 megapascals. Water potential in this region is minus 4 megapascals. Minus 2 megapascals, minus 4 megapascals. Where is more water? Right? Because minus 2 versus minus 4. Minus 4 may be a bigger number, but it's a bigger negative number. So there is less water here, more water here. I want you to remember that. It is always measured as a negative value. Okay? That's first thing I want you to remember. Second thing is that pressure of water in any location is affected by gravity. It is affected by water coming below from below, like pressure head. But the major two things that affect that pressure are what we call metric pressure and osmotic pressure. Two things, metric and osmotic. I'll simply explain these two things. So let's say the water potential is minus 2 megapascals here, right? That's what I told you, minus 2 megapascals here. That number minus 2 is coming from metric pressure and also osmotic pressure. Those two are combining and giving you that number. So what is metric pressure and what is osmotic pressure? Osmotic pressure is simply coming from salts. You apply fertilizer. What does that fertilizer do? The fertilizer will, the water, I told you the water has got little positive and little negative sides. So these ions get attracted to that water molecules and bind to them. So you will actually see there will be a central fertilizer ion, and on all around there is a big cluster shell of water molecules. All these water molecules are now bound to that ion. They are not in a free state, they are bound state. That bound state creates a situation where the plants cannot simply take that water. Okay, that is coming from what? The fertilizer salts you applied. So the more fertilizer you apply, more negative pressure, meaning the water is not actually available to plants, and it is a very common scenario. I have seen situations where people come and tell me, I got a lot of water in my pots, but my plants are wilting. Then I immediately ask them, how much fertilizer did you apply? We applied about 6.0 EC. Okay, just kidding. We were talking this morning and he said 6.0 EC, and I said that's too much. The reason why I said too much is at 6.0 EC, you are creating a drought scenario, just like a drought scenario. You are adding a lot of salts. It's like adding sodium chloride to water. And that sodium chloride water is not taken by the plants because the sodium chloride molecules are holding all the water molecules and roots can't take them. They are bound to that. That is osmotic pressure. What is metric pressure then? Metric pressure is water being held by the substrate particles. You know, the hygroscopic water, things like that. So these are the two things that create that number minus 2. Those are the two things that create the number minus 2. On the number on this side was minus 4, meaning the metric pressure was more negative. Maybe osmotic pressure was also more negative there, making that water even less available to plants compared to this one. Okay. Again, it's all pressure, it's all negative numbers, confusing, but I also want you to remember that water always moves from high pressure to low pressure, smaller negative number to bigger negative number, right? And where is this pressure coming from? It's coming majorly from two factors. One is the osmotic pressure that is coming from the fertilizer salts you apply. The other is water being simply held by the substrate particles, hygroscopic water. When the water is held by this substrate, it is not available to plants. When the water is held by the fertilizer salts, it's also not available to plants. And those two scenarios make plants feel like, oh, there is drought stress. Okay. But in any case, I think that concept, if you can understand up to this point, I think you're okay. We'll leave it there, but I wanted to really talk about one last thing about this soil, plant, water, atmosphere continuum. Now you know water potential or water pressure, and you also know what that negative numbers mean. The smaller the negative number, it's better, right? There's more water than the bigger negative number. So now let's talk about, okay, there is a plant and the plant is inside a substrate or in the soil. You add water to the soil. Now that water should get into the plant, right? How is it going inside? That's what we are trying to understand. Okay? I told you water moves because of pressure gradients. So for water to move from soil into the roots, where should be more pressure and where should be less pressure? You should have more pressure outside and less pressure in the roots, then water will go into the roots. See, it is a passive movement. There is no energy involved here. Simply there is a gradient, pressure gradient. So water is moving from soil into the root. Now water has to move from root to where? Through the stem, to the leaves. And then what happens finally? It is leaving the plant, right? So now let's talk about pressure differences. You said pressure should be more outside than inside the root. Now for water to move from root into the stem, where should be more pressure and where should be less pressure? Root should have more pressure, stem should have less pressure. From stem into the leaf, stem should have more pressure, leaf should have less pressure. And finally, from leaf into atmosphere, leaf should have more pressure and atmosphere. So now I'm giving you, you understand the concept now. Now I'm going to give you those negative numbers. Soil is at minus 0.1 megapascals. You can write it down and you can see soil is at minus 1 megapascals usually. Roots are at approximately minus 0.5 megapascals, minus 0.5 MPa, megapascals. Stem is in the range of minus 1.0 megapascals. Leaves are minus 1.5 megapascals, and finally air is about minus 70 to minus 90 megapascals. Now you see what is causing that water movement? The pull from air, atmosphere. Atmosphere is minus 70 megapascals. It is pulling the water away from the leaves. When the water from the leaves is pulled, the leaves will pull water from the stem. When the stem water is pulled, then the stem will pull the water from the root, and from the root the water is being pulled into from the soil is being pulled into the root. That continuum, that continuous path is called SPAC, soil plant atmosphere continuum. And the cause for this water movement is the dryness of the air, the minus 70 megapascals of low water pressure in the air. That is what is causing the water to move up. But again, inside the stem, water is connected by cohesive and adhesive forces. So water molecules, one molecule at a time, climb up. Think about the California, those redwood trees. They are like what, 100 meters, 200 meters tall. Each droplet, each molecule of water is moving slowly upwards because it's like you're pulling it. What is pulling it? The air is minus 70 megapascals, and it is so negative that water has to leave the leaf into the air, and that's like you're pulling it. Something is pulling the water, and every water molecule is climbing up, leaving eventually from soil outside. If you remember this concept, this is very important, because let's go back to that osmotic problem I told you. I told you that I gave you a number minus 0.1 megapascal for the soil, but if you apply too much fertilizer, that number minus 0.1 in the soil will change to minus 0.7 megapascals. When soil is minus 0.7 megapascals, root is minus 0.5 megapascals, where will water move from? From root outside, not inside, outside. So you have created what? You have created a drought scenario for plants. Although there is plenty of water, by simply adding more fertilizer, you have created an osmotic pressure, a drought pressure. It's like adding salt. This is why salts are not good. Too much fertilizer is not good. Okay, does it make sense? All of this, nice, link. Soil, plant, atmosphere continuum, water potential, pressure, the direction. Those negative numbers can sometimes be confusing, but if you remember those negative numbers, all of that. This is how water moves. This is the path. Water content, on the other hand, is something we created for ourselves. Okay, you may have a lot of water, but if that water has got a lot of salts in it, I just told you that is not going to get into the plant. The water content will tell you plenty of water. If I put a sensor, it will tell you there is plenty of water, But water potential is what drives it. Water pressure is what drives it. But if that is salt water, if that is fertilizer water, you may have a lot of water content, but it's not going to move from there into the plant. So water content is only useful for us, but for plants, it is not water content. It is water potential, pressure. Physiology of plants operate on water potential, from high pressure to low pressure.
So basically, more salt is increasing the cohesive force of water.
Oh, those salts are holding water molecules. You find a big cluster of them. Central salt molecule, all other water molecules are being tightly held by the salt. So they're not being free. So roots can't take them. That's what is happening. A big clusters and clusters of water molecules. Those salts are holding them. It's like a magnet holding all the pins, right? Pins are your water molecule and the magnet is your salt. So now the roots have to grab the pins and they need energy for that.
So we also want root to absorb those salts. So why they are not doing it?
So in this particular case, this is called soluble state, I get it. But what I'm talking about is a big cluster, sort of like an osmotic situation. But you got to keep in mind, in this case, you have put too much of fertilizer. There are ions that are freely floating, fertilizer ions, but there are also ions that are holding a lot of clusters of water. The roots are going to take those free floating soluble ions. But what the ions are also doing indirectly is holding your water molecules, lowering the pressure of the water. They lower the pressure of the water. They lower the pressure of the water. But there are also some free floating ions that roots can access. But some of the ions are forming big clusters and lowering the pressure. So both of them are happening side by side. You have to get to that balance. You have to reduce those clusters, make the more water available. At the same time, more ions are also there.
So temperature does play any role?
It may because some of the ions are more soluble, meaning they may break the bonds. Sometimes, if water molecules gain that energy with higher temperature, they may break out and they may become free water again, right? So temperature may play, but again, it increases the solubility of ions.
Like we can, let's say, use warm water for plants to absorb it better.
Yeah, but if you go beyond 75, it's going to hurt root growth.
Yeah.
Right, within that range. And that's, I don't know whether you followed yesterday afternoon, I showed you a root zone heating system where we actually are using that concept. By adding more water, we are actually enhancing solubility of nutrients, and those nutrients are being now taken by the roots. So we're breaking out those big clusters, right, and making a smaller cluster so roots can actually pull. By the way, nutrients get into the roots by energy process. So yes, you have this cluster where the nutrients is holding all these ions, but the root comes in proximity. And there are many ways. There are cofactors. There is an ATP driven pathway where the one molecule goes outside from the root, pulls that element into the root. These things happen, but this is an energy driven process. For that, the plant has to spend energy. But for water, it simply goes through passively due to pressure gradients. Yeah, it's a bit complicated mechanism happening there. But bottom line, I want to tell you is if you add too much of salt, you are just imagine like they're a magnet holding all those pieces of iron, and those iron pieces are your water molecules, and they're not being available to the plants. They're being held tightly. That's what it is. Okay, I think we're right there. Maybe this is the last slide. If you're more interested in all of this, you can read the content there. The text is there for you. But if you're not interested, you can forget about it. Okay, but as long as you understand that what is that water potential, what is that pressure, what are those negative numbers mean, you're good. And also if you understand how the water moves from soil out, those numbers I gave you, negative numbers, if you understand that, that's more than enough. But if you are really wanting to know more, read through that. There are formulas to calculate that osmotic pressure. There are methods to calculate metric pressure in there, but that can be too much for you, for some of you, not all of you. Okay. Let's see what else is here. I think that's the last one. Okay. Yeah, go ahead, ask me questions. We have some time, couple minutes.
So can you explain what is meant by pressure potential?
Oh yeah, sure. So there are, hydrostatic pressure. For example, if you are a soil physicist, you will see sometimes there's a lot of water. I was told that what is the term they're using here? It starts with capital T. The region is called Tarai. What does Tarai means? Abundance of water, right? Abundance of water. Where is that abundance coming from? From the ground, right? You have water right in the ground. That's pressure of water coming upwards. That's called hydrostatic pressure. But in parts, you don't see that. That's why it's negative. Gravity is another one that affects the pressure, the water pressure, but gravity in small parts is not a big deal. If you're really looking at the effect of gravity, you have to go for deep soils. So gravity and pressure potential are two things that we kind of exclude from that big water potential. The remaining two things are matric and osmotic. And I talked about what matric is and what osmotic is. But you also asked what pressure potential. The Terai is an example of is water is coming out. Sometimes you will see water actually coming out of the soil. It's too much. The aquifer is so close, it's positive pressure pushing water up. That affects. So these are all negatively affecting the water potential. That pressure potential positively influence. You got more pressure means pressure potential means you got more water pressure. That means there's a lot more water there. That's a good thing, but you don't see that in parts, right? That's only in field soils. That's what pressure potential is. Okay. Any other questions? This is a tough chapter. I get it. The last few slides were a little bit tough, but as long as you get that concept into your minds, what is water content, what is water potential, what is water molecule, why it is negatively charged versus slightly positively charged, what are the advantages of that, things like that, it'll be really useful. But we'll dive into irrigation concepts. We'll probably use some of these concepts when we talk about that applied stuff. Like always, the first chapter is always a little bit basics. The second chapter in that particular subtopic is more about applied stuff. So we're going to use this concept and we'll learn a little bit. But this afternoon we'll do a tutorial on soil as substrates. Okay, some simple calculations. Please do come, and you can ask your friends who have been participating in the tutorials. You will learn more during the tutorials than during the lecture hours, because these concepts that I'm telling you, they will get cemented in your brain when you take care of those tutorials. So don't miss tutorials, okay? And that's important. So take a break, and by the way, I'm going to try and get back by 2 o'clock here. I'm going to talk to Dr. Ashutosh Singh and ask me to bring me here by 2. I'll be probably available here between 2 and 3. If any of you have any questions on today's chapters or yesterday's or day before, doesn't matter. Just come and talk to me one-on-one. If you didn't want to ask a question while you were in the classroom, but you want to talk to me one-on-one, just ask me some questions. Yeah, we can just sit down and chat. Yeah, go ahead.
But due to climate change, atmospheric pressures are being fluctuated now. Atmospheric pressure are being fluctuated. And the whole process of absorption of water, the process of photosynthesis depends upon absorption of water only. And absorption of water depends upon atmospheric pressure. So, due to the fluctuations in the atmospheric pressure, the SPAC system will get affected. So, how they going to manage this thing, the pressure thing in the greenhouse management?
So the atmospheric pressure is due to, of course, water vapor is one of the things, but it's mostly to the gases. It has nothing to do with water loss or anything. When I said the pressure of water in the atmosphere is minus 70 to minus 90, you know what I'm talking about? I'm basically talking about humidity, relative humidity, or vapor pressure deficit. That affects water uptake. I do not know how much of the change is there in atmospheric pressure due to climate change. Maybe there is, but I don't think that affects photosynthesis, because that is the pressure on the plant. But pressure is coming because of the gases. It has nothing to do with the water movement, though. Okay, water movement out of the plant is affected by humidity, relative humidity, vapor pressure in the atmosphere. That's what it is. Okay. But there could be an effect of high pressure or low pressure on plant growth. Somebody may have studied hyperbaric systems. They are more useful probably in space studies and NASA related studies. I'm not sure. I don't have sufficient knowledge there. Okay. Any other questions? All right, I'll see you all this afternoon, right? Okay. Yeah. You have a question? No? Okay. I'll see you in the afternoon. I'll try to come by 2 o'clock. But let me ask you, is anybody planning to come at 2 o'clock to discuss with me? You're coming? Okay. Anyone else? Okay, then I'll come here at 2 o'clock. Just in case if you change your mind, we can come and you can chat with me on any of the subjects. If you have missed something or if you have questions about it, just it's like an open session for all of you. and then we'll start our tutorials at 3 o'clock.